The question of how big the universe is compared to our galaxy seems, at first glance, like it should have a simple numerical answer, something that could be expressed as a ratio or a multiple, the way one might say that the Earth is roughly 109 times smaller in diameter than the Sun, or that Jupiter is about 11 times wider than the Earth. But the deeper one goes into the actual science of cosmic scale, the more one discovers that the question is not just about numbers. It is about the history of how human beings came to understand that there was a galaxy at all, how they discovered that the universe extended beyond it, what tools and methods allowed them to measure distances across space, and what fundamental uncertainties still remain embedded in those measurements. It is also about what we mean by the universe, because the universe as a concept has at least 3 distinct meanings in modern cosmology, each of which gives a different answer to the question of size. And it is about the profound strangeness of discovering that the visible universe, enormous as it is, may itself be only a tiny and perhaps infinitesimal fraction of a larger whole that we may never be able to observe directly. To begin, it is worth establishing what our galaxy actually is in physical terms. The Milky Way is a barred spiral galaxy, a vast gravitationally bound system of stars, gas, dust, dark matter, and other material that rotates slowly around a central axis. The most commonly cited figure for the diameter of the Milky Way's stellar disk is about 100,000 light-years, though more recent measurements using data from surveys like the Sloan Digital Sky Survey and the European Space Agency's Gaia mission have suggested that the disk may extend further than previously thought, perhaps to around 180,000 or even 200,000 light-years if one includes the faint outer structures and warped edges of the disk that trail off into the surrounding space. The disk itself is relatively thin, roughly 2,000 light-years in thickness at the location of the Sun, though the central bulge is thicker, and the overall structure is surrounded by a roughly spherical halo of old stars, globular clusters, and dark matter that extends several 100,000 light-years from the center. The total mass of the Milky Way is estimated at roughly 1 to 2 trillion solar masses, with the vast majority of that mass consisting of dark matter rather than ordinary baryonic matter. The number of stars is estimated at somewhere between 100 billion and 400 billion, depending on how one counts faint red dwarfs and other low-luminosity objects that are difficult to detect at great distances. These numbers are worth stating clearly because they set the baseline against which the size of the universe must be compared. A galaxy of this scale is already almost incomprehensibly large by any human standard. Light, travelling at roughly 300,000 kilometers per second, takes about 100,000 years to cross the Milky Way's disk. A spacecraft travelling at the speed of the Voyager probes, roughly 17 kilometers per second, would take well over 1 billion years to cross the same distance. The galaxy is large enough that the Sun, located roughly 26,000 light-years from the centre, takes approximately 225 to 250 million years to complete a single orbit around the galactic centre, a period sometimes called a galactic year. The Earth has existed for roughly 18 to 20 galactic years. The entire history of complex multicellular life on Earth fits within about 2.5 galactic years. These are scales that already strain the capacity of human intuition to process, and yet the Milky Way is, by the standards of the observable universe, a fairly ordinary galaxy. It is neither particularly large nor particularly small. Galaxies range in size from dwarf galaxies containing only a few billion stars and spanning a few thousand light-years to giant elliptical galaxies like EC 1101, which has been estimated to have a diameter of roughly 4 million light-years, or about 40 times the diameter of the Milky Way. The Large Magellanic Cloud, one of the Milky Way's satellite galaxies, has a diameter of roughly 14,000 light-years. The Andromeda Galaxy, the nearest large spiral galaxy to the Milky Way, has a diameter of roughly 220,000 light-years, making it somewhat larger than the Milky Way, though recent studies have suggested their masses may be more comparable than once thought. The point is that even among galaxies there is enormous variation in scale, and the Milky Way occupies a middle position in this range. The story of how humanity came to understand the size of the galaxy and its relationship to the larger universe is itself a long and instructive one, and it is worth tracing in some detail because the methods and difficulties involved in measuring cosmic distances are central to understanding what the numbers actually mean and how confident we can be in them. For most of recorded history, human beings had no concept of the galaxy as a distinct physical object. The band of light visible in the night sky that we call the Milky Way was recognized by many cultures, and various mythological explanations were offered for it. But its physical nature was unknown. The ancient Greek philosopher Democritus, in the 5th century before the Common Era, apparently speculated that the Milky Way might consist of very distant stars. But this idea was not widely adopted and could not be tested with the tools available at the time. Aristotle, whose cosmological framework dominated European thought for nearly 2 millennia, argued that the Milky Way was a phenomenon of the upper atmosphere rather than something located among the stars. It was not until Galileo Galilei turned his telescope toward the Milky Way in 1610 that anyone could confirm that the band of light was indeed composed of a vast number of individual stars too faint and closely packed to be resolved by the naked eye. This was a crucial observation, but it did not by itself establish the shape or size of the stellar system that contained the Sun. The first serious attempt to map the shape of the Milky Way as a three-dimensional structure was made by William Herschel in the late 18th century. Herschel's method was to count the number of stars visible in different directions, and use those counts to infer the relative extent of the stellar system in each direction. His resulting model, published in 1785, depicted the Milky Way as a roughly flattened, irregular disk with the Sun located near its centre. This model was a significant achievement, but it was wrong in important ways. Herschel's method could not account for the absorption of starlight by interstellar dust, which makes distant stars appear fainter or renders them invisible altogether, and it could not distinguish between a truly central position for the Sun and an apparent central position caused by the limited range over which stars could be detected in all directions. The problem of interstellar extinction, as it came to be called, would not be fully appreciated for more than a century after Herschel's work, and its effects systematically distorted all attempts to determine the size and structure of the galaxy during the intervening period. In the early 20th century, the Dutch astronomer Jacobus Kapteyn carried out a much more detailed version of Herschel's program, using photographic plates and careful statistical analysis to create what became known as the Kapteyn universe, a model of the stellar system that depicted it as a lens-shaped structure roughly 30,000 light-years in diameter and 6,000 light-years thick, with the Sun located near the centre. This model was widely accepted for a time, but it too was affected by the unrecognised effects of interstellar dust, and it significantly underestimated the true size of the galaxy. The breakthrough that revealed the actual scale of the Milky Way came from the work of Harlow Shapley, who between 1914 and 1919 used observations of a particular class of variable stars known as R Lyrae stars and Cepheid variables within globular clusters to determine the distances to those clusters. Cepheid variables are stars whose intrinsic luminosity is related to the period of their brightness variations by a well-defined mathematical relationship, a discovery made by Henrietta Swan-Leavitt in 1908 based on observations of Cepheids in the Small Magellanic Cloud. By measuring the period of a Cepheid's brightness variation, one can determine its intrinsic luminosity, and by comparing this to its apparent brightness as seen from Earth, one can calculate its distance. This method, known as the period luminosity relation, became one of the fundamental rungs on the cosmic distance ladder, the interlocking set of methods by which astronomers measure distances to progressively more remote objects. Shapley found that the globular clusters were distributed in a roughly spherical arrangement, not centered on the Sun, but centered on a point roughly 50,000 light-years away in the direction of the constellation Sagittarius. This led him to conclude that the Sun was not at the center of the galaxy, but was instead located in its outskirts, and that the galaxy was much larger than Kapteyn's model had suggested, with a diameter that Shapley initially estimated at roughly 300,000 light-years. His distance estimates were later revised downward when it was recognized that he had not fully accounted for interstellar extinction, and that his calibration of the period-luminosity relation contained systematic errors, but his fundamental insight that the Sun was not centrally located was correct and represented a major conceptual shift, sometimes described as a kind of Copernican revolution applied to the scale of the galaxy rather than the solar system. The question of whether the universe contained anything beyond the Milky Way was, at the time of Shapley's work, deeply contentious. This is the context of the famous Great Debate of 1920, A public discussion held at the National Academy of Sciences in Washington, D.C. between Shapley and Heber Curtis. Shapley argued that the Milky Way was the entire universe, or at least the dominant structure within it, and that the so-called spiral nebulae, fuzzy spiral-shaped patches of light visible through telescopes, were relatively small and nearby objects located within or near the galaxy. Curtis argued that the spiral nebulae were in fact independent galaxies, comparable in size to the Milky Way but located at much greater distances, a hypothesis sometimes called the island universe theory, which had been proposed in various forms since the time of Immanuel Kant in the 18th century. Both men presented evidence and arguments, but the observational data available in 1920 were not sufficient to settle the question definitively. The resolution came in 1923 and 1924, when Edwin Hubble, using the 100-inch Hooker telescope at Mount Wilson Observatory in California, identified individual Cepheid variable stars in the Andromeda Nebula, and used their period luminosity relation to determine that Andromeda was roughly 900,000 light-years away, far beyond the boundaries of the Milky Way, and therefore clearly a separate galaxy in its own right. Hubble's distance estimate was later revised to approximately 2.5 million light-years, when Walter Baade in the 1950s recognized that there were two distinct populations of Cepheid variables with different period luminosity relations, and that Hubble had been using the wrong relation for the Cepheids he observed. But the qualitative conclusion was unchanged. The universe was not confined to the Milky Way. The Milky Way was just one galaxy among many, and the spiral nebulae were independent galaxies scattered throughout a much larger cosmos. This discovery fundamentally changed the context in which the question of cosmic size could be asked. Before Hubble's work, the question of how big the universe is compared to our galaxy would have been essentially meaningless, because the galaxy was thought to be the universe, or at least the overwhelming majority of it. After Hubble, the question became meaningful and pressing, and the answer turned out to be staggering. To appreciate just how staggering, it is necessary to understand the subsequent development of observational cosmology and the measurement of cosmic distances. Hubble himself, in the years following his identification of external galaxies, made another discovery of enormous importance. By analysing the spectra of light from distant galaxies, he found that the spectral lines of most galaxies were shifted toward the red end of the spectrum, a phenomenon called redshift, and that the amount of redshift was proportional to the distance of the galaxy, with more distant galaxies showing greater redshifts. This relationship, published in 1929 and now known as Hubble's law, or more recently as the Hubble-Lemaitre law, in recognition of the independent theoretical work of the Belgian physicist Georges Lemaitre, who had predicted the relationship on the basis of general relativity before Hubble's observational confirmation, was interpreted as evidence that the universe is expanding, with galaxies receding from one another at speeds proportional to their separation. This did not mean that galaxies were flying apart through static space like fragments of an explosion. Rather, it meant that space itself was expanding, carrying galaxies along with it, a distinction that has profound implications for the measurement of distances at cosmological scales. The expansion of the universe meant that the question of how big the universe is could not be answered simply by measuring the current distances to the most remote objects. It also raised the question of whether the universe was finite or infinite in spatial extent, a question that remains unresolved in modern cosmology. What could be measured, at least in principle, was the size of the observable universe, defined as the region of space from which light has had time to reach us since the beginning of the expansion, taking into account the fact that space has been expanding throughout the time the light has been travelling. The boundary of the observable universe is not a physical barrier, but a horizon defined by the finite speed of light and the finite age of the universe. The age of the universe is determined by multiple independent lines of evidence, including measurements of the cosmic microwave background radiation, the observed expansion rate, and the ages of the oldest known stars and globular clusters, is approximately 13.8 billion years, with an uncertainty of only about 1%. This means that the most distant light we can observe has been travelling for roughly 13.8 billion years. However, because the universe has been expanding during that time, the objects that emitted that light are now much farther away than 13.8 billion light-years. The current proper distance to the most remote objects whose light is just now reaching us, which defines the radius of the observable universe, is approximately 46.5 billion light-years. The diameter of the observable universe is therefore approximately 93 billion light-years. This number, 93 billion light-years, is the figure most commonly cited as the size of the observable universe. It can now be compared directly to the size of the Milky Way. If the Milky Way has a diameter of roughly 100,000 light-years, and the observable universe has a diameter of roughly 93 billion light-years, then the observable universe is approximately 930,000 times wider than the Milky Way. In terms of volume, the difference is vastly greater because volume scales as the cube of diameter. The volume of a sphere with a diameter of 93 billion light-years is roughly 8 times 10 to the 17th power, or 800 quadrillion times the volume of a sphere with a diameter of 100,000 light-years. These are ratios so large that they're difficult to convey through analogy, but one might note that the ratio of the diameter of the observable universe to the diameter of the Milky Way is roughly comparable to the ratio of 1 kilometer to 1 millimeter, or the ratio of the distance from New York to Los Angeles to the length of a small coin. But these comparisons, dramatic as they are, apply only to the observable universe, and there are strong theoretical reasons to believe that the observable universe is only a small fraction of the entire universe. The observable universe is limited by the speed of the light and the age of the cosmos, not by the actual extent of space. Beyond the observable universe, there is almost certainly more space containing more galaxies, more stars and more matter, but the light from those regions has not had time to reach us, and because of the accelerating expansion of the universe, driven by dark energy, much of that light may never reach us at all. The actual size of the entire universe is unknown, and may be unknowable through direct observation. Several lines of evidence and theoretical argument bear on the question of how much larger the entire universe might be compared to the observable universe. One comes from measurements of the geometry of space, specifically from observations of the cosmic microwave background radiation, the faint afterglow of the hot, dense, early universe that permeates all of space. The cosmic microwave background was first detected in 1965 by Arno Penzias and Robert Wilson, and it has since been studied in exquisite detail by a series of satellite missions, including COBE, launched in 1989, WMAP, launched in 2001, and Planck, launched in 2009. These measurements have shown that the large-scale geometry of the universe is very close to flat, meaning that the rules of Euclidean geometry apply on the larger scales to a very high degree of precision. The Planck satellite's measurements, published in 2018, found that the density of the universe is within about 0.5% of the critical density that would make space perfectly flat. This finding has significant implications for the size of the universe. If the universe were positively curved, like the surface of a sphere, it would be finite in volume, and its total size could in principle be estimated from the degree of curvature. The fact that the observed curvature is so close to zero means either that the universe is exactly flat, in which case it is spatially infinite, or that it is very slightly curved, in which case it is finite but much, much larger than the observable portion. Various analyses of the Planck data have attempted to place lower bounds on the size of the universe under the assumption that it has slight positive curvature, and these lower bounds are typically at least several hundred times the radius of the observable universe, meaning that the total universe, if finite, has a volume at least millions or billions of times larger than the observable universe. Some estimates, depending on assumptions, place the lower bound much higher still. There is also a theoretical argument from the inflationary model of the early universe. Inflation is a hypothesis, originally proposed by Alan Guth in 1981 and subsequently developed by André Linde, Andreas Albrecht, Paul Steinhardt and others, which posits that the universe underwent a period of exponentially rapid expansion in the first tiny fraction of a second after the Big Bang. During this inflationary period, the universe may have expanded by a factor of at least 10 to the 26th power, and possibly vastly more in an almost inconceivably short time. Inflation was originally proposed to solve several puzzles in standard Big Bang cosmology, including the horizon problem, why the cosmic microwave background has nearly the same temperature in all directions even though distant regions of the sky were too far apart to have been in causal contact in the standard model, the flatness problem, why the geometry of the universe is so close to flat, and the monopole problem, why certain exotic particles predicted by grand unified theories have never been observed. Inflation solves these problems by postulating that the observable universe originated from a tiny, causally connected patch that was inflated to enormous size, smoothing out any initial irregularities and driving the geometry to flatness. If inflation occurred, the total universe generated by it would be vastly larger than the observable universe. In many versions of inflationary theory, the total universe is so large that the observable universe is to the total universe as a single atom is to the observable universe, or even less. These are not precise calculations, but rather indications of the orders of magnitude involved. In some versions of eternal inflation, the inflationary process never fully stops everywhere, but continues in some regions while ending in others, producing an effectively infinite number of separate regions, sometimes called pocket universes, each with its own Big Bang and its own potentially different physical constants. This scenario, if correct, would mean that the question of the size of the universe compared to our galaxy is not merely a question of large numbers, but a question about the fundamental structure of reality, with the Milky Way occupying an almost vanishingly small point in an incomprehensibly vast or infinite expanse. It is worth pausing here to note that while inflation is widely accepted among cosmologists as a component of the standard cosmological model, it is not universally accepted, and there are ongoing debates about its theoretical foundations, its predictions, and whether it is truly testable. Critics such as Paul Steinhardt, who was one of inflation's original developers but later became skeptical of it, have argued that eternal inflation in particular makes the theory unfalsifiable because it predicts essentially everything and therefore explains nothing. Other researchers have proposed alternative scenarios for the very early universe that do not involve inflation, such as bouncing cosmologies or the ekpyrotic model. These debates are relevant to the question of cosmic size because the strongest theoretical arguments for the universe, being enormously larger than the observable universe, come from inflationary models, and if inflation is wrong, or if it occurred in a more limited form than often assumed, the constraints on the total size of the universe would be different. Regardless of these theoretical uncertainties, the observational data alone establish that the observable universe is at least 930,000 times wider than the Milky Way, and there is no observational evidence suggesting that the universe ends at the boundary of the observable universe. Every observation is consistent with the universe continuing beyond what we can see, with the same basic structure, the same types of galaxies, the same physical laws, and the same large-scale statistical properties. The cosmic microwave background shows no signs of a boundary, no edge effects, no reflections, nothing that would suggest that the observable universe bumps up against a wall or a different kind of space at its edges. To put the comparison between the galaxy and the universe in more concrete terms, it is useful to consider some of the structures that exist between the scale of a single galaxy and the scale of the observable universe as a whole. The Milky Way is not an isolated object. It is part of a small group of galaxies called the Local Group, which contains about 80 known-member galaxies spread across a volume roughly 10 million light-years in diameter. The dominant members of the Local Group are the Milky Way and the Andromeda Galaxy, with the Triangulum Galaxy being the third largest. Most of the other members are small dwarf galaxies, gravitationally associated with one or the other of the two large spirals. The Local Group is itself part of a larger structure called the Virgo supercluster, or the Local supercluster, a collection of roughly 100 galaxy groups and clusters spread across a volume roughly 110 million light-years in diameter, centered approximately on the Virgo cluster, a large cluster of roughly 1,300 galaxies located about 54 million light-years from the Milky Way. In 2014, a team led by R. Brent Tully published an analysis based on galaxy peculiar velocities, the deviations of galaxy motions from the smooth expansion of the universe, which revealed that the Virgo supercluster is itself just one lobe of an even larger structure that the team named Laniakea, from the Hawaiian words meaning immense heaven. Laniakea is a supercluster containing roughly 100,000 galaxies and spanning about 500 million light-years. The boundaries of Laniakea are defined by the surfaces along which galaxy flows diverge, with galaxies on one side of the boundary flowing toward the center of Laniakea, and galaxies on the other side flowing toward the centers of neighboring superclusters. Laniakea here is not a gravitationally bound structure in the way that the Local Group or even the Virgo cluster is. Its member galaxies are not orbiting a common centre, but are rather falling toward a region of gravitational attraction called the Great Attractor, located roughly 250 million light-years from the Milky Way, in the direction of the constellations Centaurus and Norma. The Great Attractor was first identified in the 1970s and 1980s through studies of galaxy motions, and was found to correspond to a concentration of mass centered on the Norma cluster. Beyond Laniakea, the universe is organized into a vast web-like pattern of filaments, walls, clusters, and voids. This large-scale structure, sometimes called the cosmic web, was first revealed observationally through galaxy redshift surveys beginning in the 1980s, particularly the CFA redshift survey conducted by Margaret Geller, John Uchra, and their collaborators, which produced the famous map showing galaxies arranged in sheet-like structures separated by enormous empty voids. The largest known structures in the universe include galaxy filaments and walls that extend for hundreds of millions or even billions of light-years. The Hercules Corona Borealis Great Wall, identified in 2013 through gamma-ray burst data, has been estimated to span roughly 10 billion light-years, though its physical reality as a single coherent structure has been questioned. The Sloan Great Wall, identified in 2003, spans roughly 1.37 billion light-years. These structures are so large that light takes billions of years to cross them, and yet they're still small compared to the full extent of the observable universe. The voids between these structures are also enormous. Typical cosmic voids have diameters of roughly 30 to 300 million light-years, though some are larger. The Boötes void, one of the largest known, has a diameter of roughly 330 million light-years and contains very few galaxies. The KBC void, identified in 2013, may be even larger, with some estimates placing its diameter at roughly 2 billion light-years. And the Milky Way appears to be located within it, or near its edge, which has implications for local measurements of the expansion rate of the universe. All of these structures, from galaxy groups to superclusters to filaments to voids, exist within the observable universe, which as noted has a diameter of about 93 billion light-years. The total number of galaxies in the observable universe has been a subject of ongoing revision. For many years, the commonly cited figure was roughly 100 to 200 billion galaxies, based on deep field observations by the Hubble Space Telescope and extrapolations to the unobserved sky. In 2016, a study by Christopher Consolis and collaborators used a theoretical framework to estimate that the total number of galaxies in the observable universe might be as high as 2 trillion, or 2,000 billion, with the majority being small, faint galaxies that existing surveys had not yet detected. This estimate has itself been debated, and observations from the James Webb Space Telescope, which began its science operations in 2022, are providing new data that will help refine the count. Regardless of the exact number, the observable universe contains an almost incomprehensibly large number of galaxies, each of which contains billions or hundreds of billions of stars, and the Milky Way is just one of them. To return to the central comparison, if the Milky Way is roughly 100,000 light-years across, and the observable universe is roughly 93 billion light-years across, the ratio is about 930,000 to 1. But this ratio, large as it is, understates the true disparity because it compares diameters, and the relevant physical quantity for most purposes is volume. The volume of the observable universe is roughly 4 times 10 to the 80th cubic meters, while the volume of the Milky Way's disk, approximated as a cylinder 100,000 light-years in diameter and 2,000 light-years thick, is roughly 4.7 times 10 to the 62nd cubic meters. The ratio of volumes is therefore on the order of 10 to the 18th, or roughly a billion billion. In other words, if one could somehow take the volume of the Milky Way and use it as a unit of measurement, one would need roughly a billion copies of it to fill the observable universe. This comparison, however, treats the Milky Way as if it were a solid object, which it is not. The galaxy is overwhelmingly empty space, with the distances between stars typically measured in light-years. The nearest star to the Sun, Proxima Centauri, is about 4.2 light-years away. If the Sun were a basketball in New York City, Proxima Centauri at the same scale would be another basketball somewhere near Los Angeles. The average density of matter in the Milky Way is extraordinarily low by everyday standards, and the average density of the universe as a whole is even lower. roughly 6 protons per cubic meter, or about 10 to the minus 27th kilograms per cubic meter. The cosmic web structure means that matter is concentrated in filaments and clusters with vast, nearly empty voids between them, and even within galaxies and clusters, matter is concentrated in stars, planets, and gas clouds with enormous distances separating them. One way to think about the relative sizes is in terms of the time it takes light to cross various structures. Light crosses the solar system, measured as the diameter of the orbit of Neptune, in roughly 8 hours. Light crosses the Milky Way in roughly 100,000 years. Light crosses the local group in roughly 10 million years. Light crosses the Virgo supercluster in roughly 110 million years. Light crosses the observable universe in roughly 93 billion years, except that this figure does not actually represent the travel time of any light signal, because the expansion of the universe during the time the light has been travelling means that the actual light travel time for the most distant objects is only about 13.8 billion years, with the rest of the distance having been added by the expansion itself. This is one of the more counterintuitive aspects of modern cosmology, and one that is frequently misunderstood. The observable universe has a radius of 46.5 billion light-years, but it is only 13.8 billion years old. This is not a contradiction. It is a direct consequence of the expansion of space. When the cosmic microwave background radiation was emitted, the matter that emitted it was only about 42 million light-years from the matter that would eventually become the Milky Way. Over the subsequent 13.8 billion years, the expansion of space has carried that matter to a current distance of about 46.5 billion light-years, while the light it emitted has been travelling through expanding space for the entire intervening period, and is just now arriving. The discovery and measurement of the cosmic microwave background itself provides another way to appreciate the scale comparison between the galaxy and the universe. The cosmic microwave background is remarkably uniform in all directions, with temperature variations of only about 1 part in 100,000 across the sky. These tiny temperature fluctuations correspond to slight density variations in the early universe, which later grew under the influence of gravity to form the large-scale structure of galaxies, clusters, and voids that we see today. The angular scale of the largest fluctuations in the cosmic microwave background is about 1 degree on the sky, which corresponds to a physical scale. At the time the radiation was emitted, roughly 380,000 years after the Big Bang, of about 150 megaparsecs, or roughly 500 million light-years in today's expanded coordinates. The Milky Way, at 100,000 light-years across, is roughly 5,000 times smaller than the scale of the dominant fluctuations in the cosmic microwave background, and millions of times smaller than the entire observable universe as traced by that radiation. Another instructive comparison involves the number of stars. The Milky Way contains roughly 200 to 400 billion stars. The observable universe, with its roughly 200 billion to 2 trillion galaxies, contains somewhere between 10 to the 22nd and 10 to the 24th stars, or between 10 sextillion and 1 septillion stars. If the lower estimate is used, the observable universe contains roughly 50 billion to 100 billion times as many stars as the Milky Way. If the higher estimate is used, the ratio could be as high as several trillion to 1. The mass comparison is similarly dramatic. The total mass of the Milky Way, including dark matter, is roughly 1 to 2 trillion solar masses, or roughly 2 times 10 to the 42nd kilograms. The total mass of the observable universe, including dark matter and dark energy, is estimated at roughly 10 to the 53rd kilograms, giving a ratio of roughly 10 to the 11th, or about 100 billion. In other words, the observable universe has roughly 100 billion times the mass of the Milky Way, which is perhaps not surprising given that it contains roughly that many galaxies of comparable or varying size. All of these comparisons deal with the observable universe only. As discussed earlier, the total universe may be far larger, potentially infinitely so. If the universe is infinite, then the comparison between the Milky Way and the universe is not a ratio at all, but a comparison between a finite quantity and an infinite one, which is a categorically different kind of statement. Even if the universe is finite but much larger than the observable universe, as most inflationary models suggest, the ratio of the size of the universe to the size of the Milky Way would be so large as to be effectively meaningless in any practical sense. It is useful to trace the history of cosmic distance measurement in more detail, because the story of how these enormous numbers were established is not just a story of technological progress, but also a story of systematic errors, conceptual revisions, calibration disputes, and the gradual refinement of methods over more than a century. The cosmic distance ladder, as it is metaphorically called, is a sequence of methods, each of which works reliably over a certain range of distances and is calibrated against the methods that work at shorter distances. The lower rungs of the ladder are based on direct geometric measurements. The most fundamental is stellar parallax, the apparent shift in the position of a nearby star against the background of more distant stars as the Earth moves around the Sun. The parallax of a star is inversely proportional to its distance, and by measuring the parallax angle one can calculate the distance directly, without any assumptions about the star's properties. Stellar parallax was first measured successfully in 1838 by Friedrich Bessel, who determined the distance to the star 61 Cygni to be about 10.3 light-years, close to the modern value of 11.4 light-years. From the ground, parallax measurements are limited by atmospheric distortion to distances of a few hundred light-years, but the Hipparcos satellite, launched by the European Space Agency in 1989, extended reliable parallax measurements to about 1,000 light-years, and the Gaia satellite, launched in 2013, has measured parallaxes for over 1 billion stars to distances of several thousand light-years, with some useful measurements extending to tens of thousands of light-years, covering a significant fraction of the Milky Way. Beyond the range of parallax, the next rungs of the distance ladder include spectroscopic parallax, estimating the intrinsic luminosity of a star from its spectral type and comparing this to its apparent brightness, eclipsing binary systems, where the orbital dynamics of a pair of stars can be used to determine their sizes and luminosities, and the period luminosity relation for Cepheid variables and RR Lyrae stars. Cepheids, as noted earlier, were central to both the measurement of the Milky Way's size and the discovery of external galaxies. They remain one of the most important distance indicators in astronomy, usable out to distances of roughly 70 to 80 million light-years with the Hubble Space Telescope and potentially further with the James Webb Space Telescope. For distances beyond the range of Cepheids, astronomers rely on Type Ia supernovae, a particular class of stellar explosions that are thought to occur when a white dwarf star in a binary system accumulates matter from a companion star and reaches a critical mass, triggering a thermonuclear explosion that completely destroys the star. Type I. A supernovae are extremely bright, outshining their entire host galaxy for a few weeks, and their peak luminosity is remarkably consistent, making them useful as standard candles for measuring distances to galaxies billions of light-years away. It was observations of Type Ia supernovae in distant galaxies that led, in 1998, to the discovery that the expansion of the universe is accelerating, a finding attributed to the influence of dark energy and recognized with the Nobel Prize in Physics in 2011 for Saul Perlmutter, Brian Schmidt, and Adam Rees. The calibration of each rung of the distance ladder depends on the accuracy of the rungs below it, and errors can propagate upward through the chain. One of the most significant unresolved issues in modern cosmology, often referred to as the Hubble tension, involves a discrepancy between two independent measurements of the current expansion rate of the universe, known as the Hubble constant. Measurements based on the cosmic microwave background as observed by the Planck satellite, combined with the standard cosmological model, give a value of approximately 67.4 km per second per megaparsec. Measurements based on the cosmic distance ladder, using Cepheids and Type Ia supernovae to directly measure the distances and recession velocities of relatively nearby galaxies, give a value of approximately 73 km per second per megaparsec. The discrepancy between these two values is roughly 9%, and it has persisted despite extensive efforts to identify and correct potential sources of systematic error in either method. If the Hubble tension reflects a genuine difference rather than a as-yet unidentified error, it could indicate that the standard cosmological model is incomplete, and that new physics is needed to explain the expansion history of the universe. This would, among other things, affect the calculated size of the observable universe, because the size depends on the expansion rate in its history. The determination of the size of the observable universe also depends on the cosmological model used to interpret the observations. The standard model of cosmology, known as the lambda-CDM model, lambda referring to the cosmological constant, which represents dark energy, and CDM standing for cold, dark matter, describes a universe that is approximately 68% dark energy, 27% dark matter, and 5% ordinary baryonic matter, and that has been expanding at a rate that decelerated during the first several billion years due to the gravitational attraction of matter, and has been accelerating for roughly the last 5 billion years due to the repulsive effect of dark energy. Within this model, the geometry of the universe is flat to within observational precision. The age is 13.8 billion years, and the comoving radius of the observable universe is 46.5 billion light-years. These figures are model-dependent, meaning that if the model is wrong in some fundamental way, the numbers could change. However, the lambda-CDM model is supported by a wide range of independent observations, including the cosmic microwave background, the large-scale distribution of galaxies, the abundances of light elements produced in Big Bang nucleosynthesis, and the observed relationship between redshift and distance for Type 1a supernovae. No competing model currently provides as good a fit to all of these observations simultaneously. Within the lambda-CDM framework, the observable universe contains a certain total amount of matter and energy, and the distribution of that matter and energy has been mapped in progressively greater detail through galaxy surveys and cosmic microwave background observations. The Sloan Digital Sky Survey, which began observations in 2000 and has gone through several phases, has mapped the three-dimensional positions of millions of galaxies and quasars over a large fraction of the sky, revealing the cosmic web structure in extraordinary detail. The Dark Energy Survey, the Dark Energy Spectroscopic Instrument Survey, and the upcoming surveys by the Vera C. Rubin Observatory and the Euclid satellite will extend these maps further, covering larger volumes and reaching fainter objects. These surveys not only map the distribution of galaxies, but also allow measurements of baryon acoustic oscillations, a pattern of density fluctuations imprinted on the distribution of matter by sound waves in the early universe, which serve as a standard ruler for measuring cosmic distances. The characteristic scale of baryon acoustic oscillations is about 490 million light-years in today's expanded coordinates, providing a calibration check on the distance ladder that is largely independent of Cepheids and supernovae. One of the subtler aspects of comparing the size of the galaxy to the size of the universe is the question of what counts as the edge of each. As noted, the Milky Way does not have a sharp boundary. Its stellar disk fades gradually into the surrounding intergalactic medium, with the outermost detected stars and streams of debris extending to several 100,000 light-years from the centre. The dark matter halo extends even further, perhaps to 400,000 or even 600,000 light-years, depending on how one defines its boundary. Similarly, the observable universe does not have a sharp physical edge. The cosmic microwave background, which represents the earliest light we can see, was emitted when the universe was about 380,000 years old, and the matter that emitted it is now roughly 46.5 billion light-years away. But this is not a wall or a barrier. It is simply the limit of how far back in time we can see using electromagnetic radiation. Before the cosmic microwave background was emitted, the universe was opaque to light because it was filled with a hot plasma that scattered photons, preventing them from travelling freely. The transition from opaque to transparent, called recombination, marks the surface of last scattering, which is what we see as the cosmic microwave background. In principle, one could observe earlier times using different messengers, such as neutrinos or gravitational waves, which decoupled from matter at even earlier times, and there are active efforts to detect the cosmic neutrino background, though this is extraordinarily challenging with current technology. The question of what lies beyond the observable universe is, almost by definition, inaccessible to direct observation. However, it is not entirely beyond the reach of inference. The uniformity of the cosmic microwave background, the agreement of observations with the predictions of the lambda-CDM model, and the success of inflation in explaining the large-scale properties of the universe all support the conclusion that the universe beyond the observable horizon is qualitatively similar to the universe within it, with the same types of galaxies, the same large-scale structure, and the same physical laws. This is sometimes called the cosmological principle, the assumption that the universe is, on large scales, homogeneous and isotropic, meaning that it looks roughly the same everywhere and in every direction. The cosmological principle is supported by observations of the cosmic microwave background and the large-scale distribution of galaxies, both of which show the expected statistical homogeneity on scales larger than about 1 billion light-years, though on smaller scales the distribution is highly inhomogeneous, with the web of filaments, clusters, and voids described earlier. It is also worth considering the comparison between the galaxy and the universe from the perspective of time rather than space. The Milky Way is roughly as old as the universe itself. The oldest known stars in the Milky Way, found in the galactic halo and in globular clusters, have ages estimated at roughly 12 to 13 billion years, placing their formation within the first 1 to 2 billion years after the Big Bang. The galactic disk formed somewhat later, probably around 8 to 10 billion years ago, and has been continuously forming new stars since then. The Sun, at roughly 4.6 billion years old, is a relatively recent addition. By contrast, some galaxies in the observable universe are seen as they were only a few hundred million years after the Big Bang, thanks to the fact that looking at distant objects is equivalent to looking back in time. The James Webb Space Telescope has detected galaxies at redshifts above 14, corresponding to times less than 300 million years after the Big Bang, when the universe was only about 2% of its current age. These early galaxies are smaller and less organized than galaxies in the present-day universe, consistent with the hierarchical model of structure formation, in which small galaxies merge over time to form larger ones. The comparison between galaxy and universe can also be made in terms of the information content or the complexity of the structures involved. The Milky Way is a single complex system with a particular history of formation, merger, chemical enrichment, and dynamical evolution. It contains stars spanning a range of ages, compositions, and masses, organized into distinct structural components: the thin disk, the thick disk, the central bulge, the stellar halo, and the dark matter halo, each with its own characteristic properties. It has a central supermassive black hole, Sagittarius A star, with a mass of about 4 million solar masses, whose existence was confirmed by decades of observations of stellar orbits near the galactic center, and by the Event Horizon Telescope's imaging of the shadow of the black hole published in 2022. It has spiral arms maintained by density wave patterns in the disk, a magnetic field that threads through the interstellar medium, and a complex ecosystem of star formation and stellar death that cycles matter between stars and the gas from which new stars form. Each of the other galaxies in the observable universe has its own comparably complex internal structure and history. Galaxies come in a range of types, from spiral galaxies like the Milky Way and Andromeda, to elliptical galaxies that are generally older, redder, and less actively forming new stars, to irregular galaxies that lack the organized structure of spirals or ellipticals, to lenticular galaxies that have a disk but no spiral arms, to dwarf galaxies of various types. The Hubble classification scheme, introduced in the 1920s, arranged galaxies into a tuning fork diagram based on their visual appearance. But modern galaxy classification takes into account a much wider range of properties, including mass, luminosity, color, star formation rate, metallicity, gas content, nuclear activity, and environment. The diversity of galaxies in the universe is enormous, and the processes that determine a galaxy's properties, including its initial conditions, merger history, gas accretion, star formation history, and interactions with its environment, are the subject of active research using both observations and large-scale computer simulations such as the illustrious TNG, Eagle, and Fire simulations. Returning once more to the numerical comparison, it may be helpful to present it at several different levels of precision and with different caveats. If one takes the diameter of the Milky Way's stellar disk as 100,000 light-years, and the diameter of the observable universe as 93 billion light-years, the ratio is 930,000 to 1. If one uses a larger estimate for the Milky Way, say 200,000 light-years including the outer disk, the ratio drops to about 465,000 to 1. If one uses the extent of the Milky Way's dark matter halo, say 500,000 light-years, the ratio drops further to about 186,000 to 1. But even the smallest of these ratios is enormous, and the volume ratios are correspondingly many orders of magnitude larger. It is also worth noting that the comparison between a single galaxy and the entire observable universe is, in a sense, the wrong comparison to make if one is trying to understand the hierarchical structure of the cosmos. The more natural comparisons might be between a galaxy and a galaxy cluster, between a galaxy cluster and a supercluster, between a supercluster and the observable universe, and so on. At each level, there is a jump in scale of roughly 1 to 3 orders of magnitude in diameter. The Milky Way is about 100,000 light-years across. The local group is about 10 million light-years across, a factor of 100. The Virgo supercluster is about 110 million light-years across, another factor of about 10. Laniakea is about 500 million light-years across, another factor of about 5. The largest observed structures, such as great walls and filaments, are a few billion light-years across, another factor of a few, and the observable universe, at 93 billion light-years, is another factor of 10 to 30 beyond the largest individual structures. The total factor from galaxy to observable universe is on the order of 1 million in diameter, which is what we calculated earlier. The hierarchical structure of the universe means that this factor is not achieved in a single jump, but through a nested sequence of ever larger structures, each embedded in the next. The uniformity of the universe on the larger scales, as evidenced by the cosmic microwave background and galaxy surveys, means that beyond a certain scale, roughly a few 100 million to 1 billion light-years, there are no larger coherent structures. The universe becomes statistically homogeneous, meaning that any sufficiently large volume looks roughly the same as any other. The cosmic web pattern of filaments, clusters, and voids is present everywhere, but it does not organize into still larger superstructures in the way that stars organize into galaxies, and galaxies organize into clusters. This homogeneity is itself a deep and important fact about the universe, and it is one of the key predictions of the standard cosmological model that has been confirmed by observations. One more aspect of the comparison between the galaxy and the universe deserves attention, and that is the question of mass density and the role of dark matter and dark energy. The average mass density of the Milky Way, calculated as the total mass of roughly 1 to 2 trillion solar masses distributed over a volume of roughly a few times 10 to the 62nd cubic meters, is extremely low by everyday standards, but much higher than the average density of the universe as a whole. The average density of the observable universe is about 9.9 times 10 to the minus 27th kilograms per cubic meter, or about 6 protons per cubic meter. The Milky Way, despite being mostly empty space, is a region of dramatic overdensity compared to the cosmic average. This is a general feature of gravitationally bound structures. They are denser than the average, surrounded by voids that are less dense, and the contrast between overdense and underdense regions is what gives the universe its structure. The composition of the universe's total mass energy budget is another important aspect of the comparison. In the Milky Way, the mass is dominated by dark matter, which makes up roughly 80 to 90% of the total, with the remainder being ordinary baryonic matter in the form of stars, gas, and dust. In the observable universe as a whole, the total mass energy budget is dominated by dark energy, which makes up about 68%, with dark matter making up about 27%, and ordinary matter about 5%. Dark energy does not clump in galaxies or clusters. It is uniformly distributed throughout space, and its effects become significant only on cosmological scales. This is why the expansion of the universe is accelerating overall, but the Milky Way and other gravitationally bound structures are not expanding internally. On the scale of a galaxy, the gravitational attraction of matter overwhelms the repulsive effect of dark energy, and structures that are already gravitationally bound will remain so indefinitely. But on the scale of the observable universe, dark energy dominates the dynamics, driving the acceleration of the expansion and ensuring that distant galaxies will continue to recede from us at ever-increasing speeds. This brings up a final point about the future evolution of the cosmic size comparison. Because the expansion of the universe is accelerating, the observable universe will grow larger over time, in the sense that light from more distant regions will eventually reach us. But this growth will be outpaced by the recession of distant galaxies, meaning that the number of galaxies accessible to observation will actually decrease over time. Galaxies that are currently visible will eventually be carried beyond the cosmological event horizon by the expansion of space, and their light will be redshifted to undetectable wavelengths. In the far future, trillions of years from now, an observer in the Milky Way, or whatever the Milky Way has become by then, will see only the galaxies of the local group, which will have merged into a single large elliptical galaxy. The rest of the universe will be dark and empty from that observer's perspective, not because the universe has stopped existing, but because the expansion has carried everything else beyond the horizon of observability. The cosmic microwave background will have been redshifted to undetectable levels, and there will be no observational evidence of the Big Bang or the larger universe. From the perspective of that far future observer, the universe will appear to consist of a single galaxy surrounded by an infinite, dark and empty void, a situation remarkably similar to what astronomers in the early 20th century believed before Hubble's discovery of external galaxies. This is a striking example of how the observable properties of the universe depend not only on its actual structure, but also on when and where the observation is made. In the nearer-term future, the Milky Way and the Andromeda Galaxy are on a collision course, with their mutual gravitational attraction causing them to approach each other at roughly 110 kilometers per second. The two galaxies are expected to begin merging in roughly 4 to 5 billion years, with the merger process taking another 1 to 2 billion years to complete. The result will be a large elliptical galaxy, sometimes nicknamed Milkdromeda or Milkomeda, which will contain the combined stellar populations of both galaxies along with whatever remains of the smaller members of the local group that are swept up in the merger. The merger will not involve direct collisions between stars, because the distances between stars are so vast relative to their sizes, but it will dramatically alter the orbits of stars, disrupt the spiral structure of both galaxies, trigger bursts of star formation as gas clouds are compressed by tidal forces, and eventually produce a smoother, rounder stellar distribution characteristic of elliptical galaxies. This merged galaxy will still be a tiny speck within the observable universe, which at that time will still be roughly the same size or slightly larger than it is today, with the accelerating expansion continuing to carry distant galaxies beyond the horizon. The comparison between the Milky Way and the universe is, in the end, a comparison between two very different kinds of entities. The Milky Way is a specific, bounded, gravitationally bound, physical system with a definite structure, composition, and history. The universe is the totality of everything that exists, and the observable universe is the portion of that totality accessible to our observations, defined not by a physical boundary, but by the limits of light travel time and the finite age of the cosmos. The ratio of their sizes, roughly 1 million to 1 in diameter, and 1 billion to 1 in volume for the observable universe, and potentially vastly larger or even infinite for the total universe, places the Milky Way in a perspective that is at once humbling and illuminating. It is humbling because it reveals the galaxy, which is itself so large that human beings struggle to comprehend it, to be an almost inconceivably small part of a much larger whole. It is illuminating because the methods by which this comparison was established, from the first telescopic observations of the Milky Way by Galileo to the precision cosmology of the Planck satellite and the James Webb Space Telescope, represent one of the most remarkable intellectual achievements in human history, a sustained, multi-century effort to understand the physical structure of reality at the largest scales accessible to observation. The tools and methods that have been developed along the way, parallax measurements, standard candles, redshift surveys, cosmic microwave background observations, gravitational lensing, baryon acoustic oscillations, and numerical simulations of cosmic structure formation, represent a sophisticated and interlocking set of techniques that cross-check and calibrate one another, providing confidence in the overall picture, even as important details and discrepancies, such as the Hubble tension, remain under active investigation. The picture that has emerged is one of a universe that is vastly larger than our galaxy, filled with hundreds of billions to trillions of galaxies, organized into a complex web of structure, expanding and accelerating under the influence of dark energy, and potentially extending far beyond what we can observe, perhaps infinitely so. Within this immense expanse, the Milky Way is a single moderately sized spiral galaxy, home to a few 100 billion stars, one of which is orbited by a small rocky planet, on which, for a brief period of cosmic time, beings have existed who are capable of asking how big the universe is compared to their galaxy, and of arriving, through centuries of careful observation and reasoning, at an answer that, while still incomplete, is among the most profound and well-supported conclusions in all of science. The ongoing effort to refine this answer continues with new instruments and missions. The James Webb Space Telescope is observing the most distant galaxies ever seen, pushing back the frontier of the observable universe to within a few 100 million years of the Big Bang. The Vera C. Rubin Observatory, expected to begin its full survey operations in the mid-2020s, will catalogue billions of galaxies and provide new data on the large-scale structure of the universe. The Euclid satellite, launched by the European Space Agency in 2023, is designed to map the geometry of the universe with unprecedented precision, constraining the nature of dark energy and the total amount of dark matter. The Square Kilometre Array, a radio telescope under construction in Australia and South Africa, will survey neutral hydrogen and galaxies across cosmic time, providing a complementary view of the cosmic web. And proposed future missions, such as the Laser Interferometer Space Antenna, LISA, will detect gravitational waves from merging supermassive black holes in distant galaxies, providing yet another independent window on the structure and history of the cosmos. Each of these instruments will refine our understanding of both the Milky Way and the universe in which it resides. The Gaia satellite has already revolutionized our knowledge of the Milky Way's structure, dynamics, and stellar populations, revealing streams of stars stripped from accreted satellite galaxies, mapping the spiral arms with new precision, and measuring the orbital velocities of stars throughout the disk and halo. These observations have led to a more detailed picture of the Milky Way's formation history, showing that the galaxy was built up through the accretion of smaller galaxies over billions of years, with major accretion events such as the Gaia-Enceladus sausage merger occurring roughly 8 to 11 billion years ago, and leaving distinctive signatures in the orbits and chemical compositions of stars in the inner halo. The interplay between observations of our own galaxy and observations of the universe at large is a defining feature of modern astrophysics, because the Milky Way serves as a laboratory for studying galactic processes up close, while the universe provides a statistical sample of galaxies at all stages of evolution, allowing general principles to be extracted and tested. The question of how big the universe is compared to our galaxy is therefore not a static question, with a fixed answer, but an evolving inquiry that has been progressively refined over more than a century of observation and theory. The answer has changed dramatically from the pre-Hubble view in which the Milky Way was the entire universe, to the current understanding in which it is one of perhaps 2 trillion galaxies in an observable universe roughly 1 million times wider than itself, with the total universe potentially vastly larger still. Each step in this progression has been driven by improvements in observational technology, theoretical understanding, and the development of new methods for measuring cosmic distances. And each step has revealed a universe more vast, more complex, and more structured than the previous generation of astronomers had imagined. What remains striking about this progression is how consistently it has moved in one direction, toward a larger and larger universe. At every stage, the prevailing estimate of the size of the cosmos has been revised upward, sometimes by orders of magnitude. The Herschel universe was smaller than the Kapteyn universe, which was smaller than the Shapley galaxy, which was smaller than the Hubble universe of external galaxies, which was smaller than the universe implied by the discovery of the cosmic microwave background and the measurement of the Hubble constant, which may itself be smaller than the total universe implied by inflation. Whether this trend will continue, whether future observations will reveal that the universe is even larger than currently estimated, or whether some new understanding will set an upper bound on its size, is an open question. But for now, the best answer science can give to the question of how big the universe is compared to our galaxy is. The observable universe is roughly 1 million times wider and 1 billion times larger in volume, and the total universe may be incomprehensibly larger still, and the Milky Way, vast and complex as it is a single structure within this expanse, distinguished not by its size but by the fact that it happens to be the one we inhabit and the one from which we look out at all the rest. The deep irony and intellectual richness of this situation is that the very smallness of our galaxy within the universe is what makes the universe knowable. If the Milky Way were the entire universe, there would be no cosmic microwave background, no redshifting of distant galaxies, no large-scale structure to map, no expansion to measure. It is precisely because the universe is so much larger than the Milky Way that it contains the structures and signals that allow us to determine its size, composition, and history. The disparity in scale between galaxy and universe is not just a fact to be marvelled at, but a precondition for the existence of the science that reveals it. The expansion of space, the cosmic microwave background, the distribution of galaxies, the acceleration driven by dark energy, all of these phenomena exist because the universe is far, far larger than any single galaxy, and all of them provide the evidence from which the size of the universe is inferred. This interconnection between what we observe and the conditions that make observation possible is one of the recurring themes in modern cosmology. It is related to, though distinct from, the anthropic principle, which notes that the observed properties of the universe must be compatible with the existence of observers. Without taking a position on the philosophical implications of such principles, it is worth noting as a straightforward observational fact that the universe we observe is one in which galaxies like the Milky Way exist, in which stars like the Sun form, in which planets like the Earth coalesce, and in which the chemical elements necessary for complex chemistry and biology are produced in the nuclear furnaces of stars and distributed through the interstellar medium by supernova explosions. All of this happens within a universe that is structured on the larger scales by the interplay of gravity, dark matter and dark energy, and that is old enough and large enough for billions of galaxies to have formed, each containing billions of stars, many of which are likely orbited by planets. The size of the universe compared to the galaxy is not just a measurement, it is a description of the arena in which all known physical processes occur and all known structures exist. In closing, it is perhaps fitting to return to the most concrete version of the comparison. The Milky Way is a disk of stars roughly 100,000 light-years across. The observable universe is a sphere roughly 93 billion light-years across. The ratio of diameters is about 930,000 to 1. The ratio of volumes is about 8 times 10 to the 17th to 1. The total universe may be vastly larger. These numbers are the product of centuries of observation, measurement, theory and debate, and they represent one of the most fundamental facts about the physical world that human beings have ever established. They define the scale of reality as we currently understand it, and they place our galaxy, our star, our planet and ourselves in a context that is, by any measure, extraordinarily large.